First of all, I'd just like to say thank you to the organisation and organisers for having us here. And I'm going to talk about the characterization of inks for electrochemical sensor applications. And it's basically an electrochemist perspective to performance reporting. And this reporting is typically what you have in a technical data sheet, or as what I want to start introducing, an electrochemical data sheet. So first of all, the company is Sun Chemical. It's a global company of about 20,000 employees, not including our parent company, DIC, which is based in Japan. It's a global paste and ink manufacturer for all different applications, from coatings, textiles, packaging, electronics. And within that group, we have the materials for electronics. We have stuff like high-tech graphics and coatings, materials for PCB manufacturing, electronic materials for flexible hybrid electronics, electronic materials for biosensors, foams and PSA tapes for electronic assemblies, electronic materials for solar applications. And the part I'm involved in is the electronic materials for biosensors. So where the division I'm based in is in the UK, and it's in a place called Midsummer Norton, and it's about an hour away from Bristol, just south. So electronic materials for biosensors, just as a recap, biosensor, the typical one everyone knows, is the blood glucose biosensor for diabetics, including continuous. Is it still working? Does it still sound? Yeah. Sorry. So the typical one is to prick your finger, have a blood sample, it goes on a strip, and then you have a reading for your glucose. Also in continuous glucose monitoring, which is what you have when you have inside your arm for monitoring glucose, but it's other applications from measuring potatoes, soil samples, any other type of biological analyte in the body or in an environment. So we have a range of materials. We have carbon paste, we have mediated carbon paste, platinum paste, gold paste, silver silver chloride paste, and dielectrics. Now, it's very hard to differentiate different carbons. And sometimes I get asked, what's the best ink you have for electrochemistry? And I go, how long is a piece of string? It's not something you can answer that easily because there's so many different types of applications and techniques. It all depends on the design. There's a whole range of things that come into it. And the one type of area I'm going to be focusing on is the more typical one, which is chronoampermetric type based sensors. So this is just a small selection of the Sun Chemical range of carbons, and there's quite a few of them. And it's very hard to say to someone which one is best for their purposes. They have different ratios of carbons to graphites to resins. And some of these have been developed by us, and some of them we've developed for customers. Now, customers will get the material and go, yes, it works. They'll say briefly what they're trying to do as an end result, but that's it. They don't tell us what conditions they're using, what mediators they're using, nothing. So it's very, very hard to actually say this material is good for this, or this material is good for this. And the other thing that we don't want customers to do is keep trialing carbon after carbon after carbon. It's expensive, especially for startups, trying to evaluate all these materials to find the best one. So typically when people pick a material, they normally look at the technical data sheet. Now, this is one of our technical data sheets. It's quite representative of most companies and how they present their data. You have your typical properties, pigment type, viscosity, solids, all good for the screen printing process, the coverage, dry film thickness, and there's other things about curing, etc. You will always see here sheet resistance, and it's normally presented in ohms per square at normalized to 25 microns. Just to give you just a brief update, most people know this already. So the sheet resistance, you normally have some sort of meander track. You will have a probe and you'd measure resistance from the entire material. You will measure the thickness of the print, and then you'll work out what the resistance is per what we call theoretical squares of the design. And it's normalized to 25 microns. Now, this is really good information if you're doing conductive materials. Not very good for electrochemistry. And it's basically, this is one of the issues with the industry is the data that we present on the technical data sheet is a hangover from the conductive industry. Just to, before going any further, the studies are all carried out using a ferrocyanide. The reason I chose ferrocyanide is it's a very common used mediator. It's one of the go-to ones for electrochemists as a starting principle, and pretty much most students tend to use it and are quite familiar with it. And it's a redox mediator, so it oxidizes and reduces, and you can do it multiple times, and it can be used in complexes with enzymes. So I get inquiries, and especially from the commercial team going, we have a customer that needs a product and they wanted resistance of X, normalized resistance at 25 microns. And the first thing I say is, what's the end application? Are they trying to do conductive tracks? Are they trying to do biosensors or electrochemistry? If the answer is electrochemistry, I say, please set up a meeting. And the reason why is the correlation between resistivity and electrochemistry is very poor. I've got a couple examples here of 3 different inks. I do apologize for this one. This does have a sort of a spike in it. This is from a printing process, not material. And you can see here, you've got the oxidative. It comes about 10. I'm not going to go into details about going from baseline and stuff like that, but it's just give you representations. You have one which is quite low at 40, one at 60, and one at 30. And you can see the one at 60 actually gives a much higher oxidation peak, even from baseline, compared to the other two. And this one is 30 ohms per square at 25 microns. So it's not really any relationship. And the reason for that is you can make a really conductive paste by chucking loads of polymer. You cure it, the polymer tightens. You have all those materials coming together, making a lovely connective track. Electrochemistry isn't going through material. It's a surface-related material. So the surface is what's important, not through the material. So you may have a company that gives you cyclical tamograms. Now, there's a time and a place for cyclical tamograms. It's a very powerful tool. If anyone doesn't know, it's when you run a voltage over time and you measure the current produced. But you can have different scan rates, and with different scan rates, you have different intensities. Also, if you have luck, there's also a drift in your peak oxidation. So it doesn't really tell you that much. It's very good for if you have a design and you want to try and match a carbon ink that you've already got to something else and trying to get the best candidate to match it. If you're a startup and you start from scratch, or if you're a PhD student or something like that, and you try and make a biosensor from scratch, this doesn't really tell you much information. It tells you whether the actual mediator in a system is reversible, and it also tells you the peak-to-peak separation. But this also does change depending on the actual design. If it's a 3-electrode system, it's a 2-electrode system, all sorts of things. Also, this is another example of a cyclical tammetry. So these two inks have very different compositions. They have the same materials, but the ratios between the carbon, the graphite, and the resin are completely different. But from the cyclic voltammogram, you can't really tell much. So what we're trying to do is present the data in a different way. And the first thing we do is we tell them what design we're using. And if they want a CAD drawing so they can use this design for their initial experiments, we're happy to give it to them. We tell them what the materials are used. So we got a silver chloride, which is used for reference, and also the conductive tracks, and also a conductive track under the counter electrode. We tell them which dielectric. So if they have any questions, especially the hydrophobicity of the dielectric, we tell them everything. The only thing we're going to vary in our experiments is the carbon. So we're going to do what we call a voltagram. Now, we're going to hold it at a set voltage. The voltage we hold it at all depends on the actual mediator. If you want to reduce the mediator, or if you want to oxidize it, we will hold the potential at different voltages. We will take chronoamp metric taken at different voltages. So we'll do a series of voltages, and it will take a reading from those chronoamps at certain times. And we will then get a voltagram from those readings. And we'll use separate and fresh electrodes for every single one of those readings. So for the ferrocyanide, we're going to hold it for set time at minus 0.6 volts for 60 seconds. Why are we doing this? It's to replicate what's happening if it's used in conjunction with an enzyme. So we are actually holding it at minus 6 volts. We have a set concentration mediator. And we're just basically going to reduce that mediator in the same way if you had a really good system where the enzyme is fully reduced in the whole system. We then get chronoampic measurements, and we will start from 0.0 volts and then increments up to 0.6 volts. And we'll take the readings at 5, 10, 15, 20, and then we produce our voltammogram. So here we have the P4, which was in our earlier example with the cyclic voltammogram, and we have the D3. Straight away you can see at 5 seconds, there's a difference. This is something that the cyclic voltammogram didn't tell us. So this is how we want to represent our data, is via voltammograms, showing which one's best for what type of mediator. We chose a selection of times, 5, 10, 15, and 20, because different reactions will take different times. Blood glucose, for instance, you don't want to wait 20 seconds to get a result. It's normally 5 to 10 seconds. And then just compare again. So we had our P4, which here is just under 10 microamps, compared to a cyclic voltammogram. And the main thing to notice is only one of them really tells us roughly 10, but it's not very good. And also where it starts to level off, that is where our best potential for this mediator is. It's roughly about 0.29 volts, which doesn't equilibrate anywhere in the cyclic voltammograms. So we're telling the end user what voltage to use a mediator with this material. There's an argument that you could do this. This is a static system. By static, I mean it's just deposited liquid onto the actual electrode. It's not in a stirred solution where you can continually get in a dissolved, you're continually displacing the mediator and solution. But still, it doesn't tell you the actual sensitivity. So here, you can see here we got the voltammograms. And then we got a calibration curve. So you've actually got different concentrations of, sorry, that should be ferrocyanide, not ferrocyanide, in these conditions. And you can actually get a nice linear graph. So you can actually see by concentration of what type of result you should get. So what can you get from this? We actually tell in the end user what kind of sensitivity they can get, which potential is optimum for this mediator, albeit it is based on that design. And I said, if they want that design to start their work, we're happy to give the CAD drawings. It'd be a nice start for them, and then they can change their design accordingly. And how we can actually represent the data. So in the previous slides, we give them the actual working area measurements. So we can actually present the sensitivity of it in microamps per millimoles of the mediator at 5 seconds per millimeter squared. So they have a set design, they have different working electrodes sizes. They can actually work out what type of, they can predict or get a good estimate of what kind of signal they will get. We also give applied potential, a minimum applied potential for the oxidative, maximum for the reductive. And the pH range, as we do a series of pH ranges, albeit it's not the widest, we are going to extend the pH range to see if that does have an effect, but it gives them a very good starting. You may also ask, well, wouldn't they always go for the highest one? We had cases where we've had customers that want an ink, but sometimes the sensitivity is too high. And by too high, I mean, they have a device, maybe it's a blood glucose device, which has a potentiostat built into it, but it's a single potentiostat with a certain range. If the sensitivity is too high, it goes out of that range of the potentiostat, which isn't good. So they can go for a lower one. So some of the things that they can get from this data. Also, what they can do with it is, for instance, in here we have ferrocyanide. You have your enzymatic substrate, and they can predict what to do. So if they have a glucose oxidase, or if they have a glucose dehydrogenase, or some variant of the enzyme, they can actually get it as long as they know what the ratio of moles produced by the enzyme go into the mediator is. It gives them a very good idea of what kind of signal strength they will get. So yeah, so summarize this part of it. Sensitivity data being presented in microamps per millimolar mediator per millimeter squared. The end user can actually get a really good approximation. And they can actually see whether they're getting a correct response. They can check to see if the enzymatic unit on a sensor is too low. If it's too low, then you haven't got a complete transformation of the end product, so you're not getting full potential. With ferrocyanide, as I said, we use it as a very common mediator that likes to be used. But we're not going to stop there. We're going to do various quinones, ferrocyanides, ferrocines, thiones, and ruthenium complexes. Now, if you do have any suggestions of typical mediators, which you would be interested, please find me after this or in lunchtime, or contact me. It's philip.nicholas@sunchemical.com. Any suggestions would be absolutely welcome. So that's for the working electrodes. So we've started some studies in that, but what about stuff like silver chlorides? This is a huge challenge as well, because we don't know what the end user, again, is doing. If they're oxidizing it, are they in a reductive system or pH? We don't know. And this becomes more critical for stuff like continuous glucose monitoring, where we need to see if the silver chloride is actually suitable for up to 2 weeks without losing its resistivity. Again, this is an example of our selection, and you can see there's a huge variety. They've all got different ratios of silver to silver chloride. Sometimes you'll pick the silver chloride with the least amount because it's a bit cheaper. But if it all depends on what you're trying to do. We do have some explanations of why you would use it, but again, there's no data towards it. So what we're going to do as part of the electrochemical data sheets is we are going to be running tests where we have a 2-electrode system with a carbon and the silver chloride working as the combined counter reference electrode. We're going to get that print. We're going to hold it at minus 0.6 to start with and run it for 2 weeks. Then we can see what the current is at beginning and at different intervals, and see if there is actual reduction in strength or if it goes up. We can monitor to see what the stability of that resistivity, of that, how it works as a reference electrode. We're also going to do it at minus 0.3, 0, plus 0.3, and plus 0.6. This will give us a lot of information, which we can present on these electrochemical data sheets and give the end user a lot of data so they can choose the correct material for their end application. So in summary, the electrochemical data sheets provide the best user with the best candidate or candidate materials to use for the application. And in addition to this, we're also going to be providing stuff like solvent resistance to numerous solvents. This is coming more crucial, especially with more exotic mediators, where they're using some very unique solvents, which some of the inks just cannot hold. Adhesion to wide selection of substrates and also flexibility data. Flexibility is a lot of the actual manufacturing of biosensors these days need to be bent to go into needles if they're for continuous glucose monitoring. So that information we're trying to all gather up and hopefully give the end user the best candidate to start with for their application. And thank you for listening.